Right now, as you watch this video, you might think you're sitting in three-dimensional space length, width, and height, defining the boundaries of everything that exists. But cutting-edge physics suggests something extraordinary. There could be 6, 7, or even 10 additional spatial dimensions curled up so tightly around every point in space that they remain completely invisible to your senses, yet fundamentally shape everything you experience. We've always assumed that the 3 dimensions we observe represent the totality of spatial reality. We measure objects in terms of their length, width, and height. We navigate through space by moving forward and backward, left and right, up and down. Our entire understanding of geometry, physics, and existence itself is built on the foundation of 3 spatial dimensions plus time. We were profoundly wrong about the fundamental architecture of reality. Here is what makes this revelation so staggering. These hidden dimensions aren't theoretical curiosities dreamed up by ivory tower physicists. They're mathematical necessities that emerge from our most successful theories of fundamental physics. String theory, our best candidate for a unified theory of quantum mechanics and gravity, requires the existence of extra dimensions to achieve mathematical consistency. Without these hidden spatial dimensions, the equations that describe reality at its most fundamental level simply don't work. The mathematics behind dimensional hiding are mind-bending in their implications. Einstein's general relativity operates in 4 dimensions, 3 of space plus time. But string theory requires 10 or 11 dimensions total for mathematical coherence. Where are these missing 6 or 7 dimensions? They're here, right now, curled up into geometric structures so small that they exist at every point in space, but remain below the threshold of direct detection. Leading theoretical physicists like Lisa Randall at Harvard, Greene at Columbia, and Michio Kaku have spent decades developing the mathematical frameworks that describe how extra dimensions could hide in plain sight. Their calculations reveal that dimensions can be compactified, rolled up into such tiny geometric configurations that particles and forces experience their effects without our 3-dimensional senses ever detecting their presence. But perhaps most unsettling is the growing experimental evidence that these hidden dimensions might not be merely theoretical. The Large Hadron Collider has detected hints of extra-dimensional physics through missing energy signatures that suggest particles might be escaping into hidden spatial dimensions during high-energy collisions. Gravitational anomalies in our solar system might be explained by gravitational leakage into extra dimensions that we cannot directly perceive. The implications stretch far beyond abstract physics. If extra dimensions exist, they could harbor entirely different forms of matter, energy, and perhaps even consciousness that remain completely invisible to us while existing in the same location we occupy. You could be surrounded right now by complex structures, advanced civilizations, or fundamental forces operating in spatial dimensions that your 3-dimensional biology cannot access or detect. Tonight, we'll explore the mathematical evidence for hidden dimensions, examine the experimental hints that suggest their reality, and confront the profound implications of living in a universe where the majority of spatial reality remains hidden from direct observation. We'll journey through string theory's requirements for extra dimensions, investigate how dimensions can hide through compactification and topology, and discover why some of the universe's greatest mysteries, dark matter, dark energy, and the weakness of gravity, might be explained by the existence of spatial dimensions we cannot see. We'll examine how particle accelerator experiments hint at extra-dimensional physics, explore why gravity might leak into hidden dimensions and appear weak in our 3-dimensional space, and investigate the possibility that parallel universes could exist just millimeters away from us in high-dimensional space, but remain completely inaccessible to our limited dimensional perception. By the end of this exploration, you'll understand why some of the most brilliant minds in physics believe that our three-dimensional experience represents only a tiny fraction of spatial reality, why the universe might be hiding the majority of its geometric complexity from our observation, and what it means for consciousness to exist within a small subset of a vastly larger dimensional landscape. This isn't science fiction or speculative fantasy. These are mathematical requirements that emerge from our best theories of fundamental physics, supported by growing experimental evidence and offering potential explanations for some of the deepest mysteries in cosmology. The hidden dimensions aren't in some distant realm. They're right here, integrated into the fabric of space at every point, influencing the behavior of particles and forces in ways we're just beginning to understand. If you're ready to discover how reality extends far beyond the three dimensions you can perceive, subscribe and hit the thumbs up button. And here is a question that will change your perspective forever. If you could suddenly perceive all the hidden spatial dimensions that surround you right now, how dramatically different would reality appear? Share your thoughts in the comments. I'll pin the most mind-expanding response. The mathematical evidence for dimensional hiding is about to reveal why our three-dimensional experience might be like seeing the shadow of a vastly more complex, geometric reality that extends through spatial dimensions our senses cannot detect. What you're about to learn will transform your understanding of space, reality, and your place within a universe that may be far stranger and more complex than you ever imagined. Now let us begin our journey into the hidden dimensions that could be surrounding you at this very moment. Chapter 1. Dimensional Foundations. You experience space as three-dimensional because your consciousness evolved within what might be merely the surface layer of a far more complex geometric reality. Every object you see, every movement you make, every physical interaction you observe operates within three spatial dimensions that could represent just a tiny fraction of the total dimensional structure that defines the true architecture of the universe. The concept of spatial dimensions beyond our direct experience isn't new to mathematics, but it's only recently that physics has demanded their existence as requirements rather than abstract possibilities. In mathematics, a dimension represents an independent degree of freedom for movement or measurement. A line is one-dimensional. You can only move forward or backward along its length. A plane is two-dimensional. You can move in two perpendicular directions. Our familiar space is three-dimensional because you can move in three mutually perpendicular directions: forward-backward, left-right, and up-down. But there's nothing in mathematics that limits spatial reality to exactly three dimensions. Four-dimensional, five-dimensional, or even infinite-dimensional spaces are mathematically well-defined and completely consistent geometric concepts. The question isn't whether higher-dimensional spaces are mathematically possible. It asks whether physical reality actually utilizes more spatial dimensions than the three we directly observe. Minkowski, S. 1907 formulation of spacetime united Einstein's three spatial dimensions with time to create four-dimensional spacetime, proving that physics already operates in more than three dimensions. Special and general relativity require four-dimensional mathematical frameworks to accurately describe motion, gravity, and the geometry of space and time. This established the precedent that physical reality might possess more dimensional complexity than human perception directly experiences. The mathematics of higher dimensions reveals extraordinary geometric possibilities that don't exist in three-dimensional space. In four spatial dimensions, you could tie a knot in a rope and then untie it without cutting the rope or moving the ends. The extra-dimensional freedom allows the rope to move through the fourth spatial dimension in ways that make the knot disappear. Spheres can be turned inside out without tearing or stretching in four dimensions. Objects can be completely removed from closed boxes without opening the boxes by moving them through the fourth spatial dimension. Theodore Kaluza's 1919 proposal was the first serious attempt to use extra dimensions in fundamental physics. Kaluza discovered that if space-time possessed 5 dimensions instead of 4 spatial dimensions plus time, then Einstein's equations for gravity automatically incorporated electromagnetic theory. This revolutionary insight suggested that apparently separate fundamental forces might actually be different aspects of geometry in higher dimensional space. Oscar Klein refined Kaluza's theory in 1926 by proposing that the 5th dimension could be compactified, rolled up into a tiny circle at every point in space, so small that it remains invisible to ordinary observation. Klein's calculations showed that a dimension could have a circumference on the order of the Planck length, about 10 to 35 meters, making it undetectably small while still influencing the behavior of particles and forces. This compactification mechanism provided the first mathematical model for how extra dimensions could exist without contradicting our 3-dimensional observations. If additional spatial dimensions are curled up into geometric structures smaller than atomic nuclei, then particles moving through ordinary 3-dimensional space would also be moving through these hidden dimensions, without our instruments detecting the extra-dimensional motion. The topology of compactified dimensions offers mind-bending possibilities for hidden geometric complexity. Extra dimensions could be curled up into circles, spheres, tori, or far more exotic geometric shapes called Calabi-Yau manifolds. Each different compactification geometry would create different physical effects, potentially explaining why particles have the specific masses and interaction strengths we observe. Felix Klein's work on non-Euclidean geometry in the late 19th century established mathematical frameworks that became essential for understanding higher dimensional spaces. Klein-Bottle topology demonstrates how surfaces can have only one side when embedded in 4 dimensions, a property that seems impossible in 3-dimensional thinking but becomes natural when extra spatial dimensions are available for geometric complexity. Riemann's broader investigation of curved, higher dimensional spaces provided the mathematical foundation that Einstein later used for general relativity. Riemann demonstrated that geometry in higher dimensions could have curvature properties that don't exist in lower dimensional spaces, creating the mathematical tools necessary for describing how extra dimensions might be curved and hidden while still influencing physical phenomena. The concept of dimensional hiding through compactification isn't merely abstract mathematics. It has specific physical implications that can be experimentally tested. If extra dimensions exist, then particles could have momentum components in the hidden dimensions that would appear as quantized energy levels in our 3-dimensional observations. The size and shape of compactified dimensions would determine the specific energy scales at which extra-dimensional effects become detectable. String theory emerged in the 1970s as the first comprehensive physical theory that not only allowed extra dimensions but required them for mathematical consistency. Unlike point particle theories that work fine in 3 spatial dimensions, string theory demands exactly 9 spatial dimensions plus time a total of 10 dimensions for the mathematics to remain anomaly-free and physically meaningful. The critical insight is that particles aren't really particles at the most fundamental level. They re-vibrating strings or membranes in higher dimensional space. Different vibration patterns of these fundamental strings in the extra dimensions correspond to different particle types we observe in 3-dimensional space. The electron, photon, quark, and every other fundamental particle represent different vibrational modes of strings moving through all dimensions of space, including the hidden ones. Modern string theory has evolved into min theory, which requires 11 total dimensions, 10 spatial dimensions plus time. This 11-dimensional framework provides a unified description of all fundamental forces and particles through the geometry and topology of higher dimensional space. The apparent complexity of particle physics in 3 dimensions emerges from the geometric simplicity of string and membrane dynamics in 11 dimensions. The mathematical necessity for extra dimensions in string theory isn't arbitrary. It emerges from deep requirements for mathematical consistency. String theories in fewer than 10 dimensions contain mathematical anomalies that make them inconsistent as physical theories. Only in exactly 10 dimensions do all the anomalies cancel out, creating a mathematically consistent framework that could describe physical reality. But the requirement for extra dimensions extends beyond string theory. Kaluza-Klein theories, supersymmetric models, and theories of quantum gravity all point toward the necessity of spatial dimensions beyond the three we observe. The convergence of multiple independent theoretical approaches on the requirement for hidden dimensions suggests that extra-dimensional physics represents a fundamental aspect of reality rather than an arbitrary theoretical choice. The geometric complexity possible in higher dimensions offers potential explanations for many observed features of particle physics that appear mysterious from a three-dimensional perspective. Why do particles have the specific masses they possess? Why are there exactly 3 generations of fundamental particles? Why does gravity appear so much weaker than the other fundamental forces? Extra-dimensional geometry could provide natural explanations for these observations through compactification details and higher-dimensional physics. As you contemplate the possibility that you're embedded in higher-dimensional space right now, consider that every physical process occurring in your body involves particles that could be vibrating through hidden spatial dimensions. The chemical bonds holding your molecules together, the electromagnetic forces enabling your neural activity, and the gravitational field keeping you on Earth's surface all might depend on the geometry of spatial dimensions you cannot directly perceive. The mathematical foundations for dimensional hiding are now well established, but the physical evidence requires much more sophisticated investigation. We must explore how experimental physics is beginning to probe the reality of extra dimensions through particle accelerator experiments and astronomical observations that hint at higher dimensional phenomena. Chapter 2. String Theory's Requirements. String theory didn't choose extra dimensions arbitrarily. The mathematics of the theory forced physicists to accept that reality must possess more spatial dimensions than we observe, or else the fundamental equations describing matter and energy become mathematically inconsistent and physically meaningless. This represents one of the most extraordinary requirements in the history of physics. Extra dimensions aren't just possible, they're necessary. The crisis that led to string theory began with attempts to reconcile quantum mechanics and general relativity. These two foundational theories of modern physics were perfectly within their respective domains, but they become mathematically incompatible when applied to extreme conditions like black hole singularities or the moments immediately following the Big Bang. Quantum mechanics describes matter and energy in terms of discrete packets and probability distributions, while general relativity describes gravity as smooth curvature in four-dimensional spacetime. Early attempts to quantize gravity, to create a quantum mechanical description of gravitational forces, consistently produced infinities and mathematical inconsistencies that couldn't be resolved through standard techniques. The calculations literally broke down, yielding nonsensical infinite results for physical quantities that should be finite. These mathematical disasters suggested that point-particle models of matter were fundamentally inadequate for describing reality at the deepest levels. String theory emerged as a potential solution by replacing point particles with one-dimensional vibrating strings. Instead of particles being infinitesimally small points in space, fundamental entities became extended objects, strings, that could vibrate in different patterns. This seemingly simple change from zero-dimensional points to one-dimensional strings had profound mathematical consequences that eventually required extra spatial dimensions. The mathematical breakthrough came when physicists discovered that string theory could potentially eliminate the infinities that plagued point-particle quantum gravity. The extended nature of strings provided a natural cutoff for ultraviolet divergences, The problematic infinities that arose when calculations involved arbitrarily high energies or arbitrarily short distances. String interactions remain mathematically well-behaved in regimes where point particle theories broke down completely. However, this mathematical success came with an unexpected price. The equations of string theory only remained consistent in specific numbers of spacetime dimensions. Early calculations showed that bosonic string theory, the simplest version involving only force-carrying particles, required exactly 26 spacetime dimensions for mathematical consistency. Later refinements incorporating fermionic matter particles reduced this requirement to exactly 10 spacetime dimensions. The dimensional requirement isn't a matter of preference or convenience. It emerges from deep mathematical constraints on the theory's internal consistency. In fewer than 10 dimensions, string theory develops quantum anomalies, mathematical inconsistencies that violate fundamental principles like unitarity and gauge invariance. These anomalies would render the theory physically meaningless, producing violations of probability conservation and other requirements for a sensible physical theory. Michael Greene and John Schwarz demonstrated in 1984 that these quantum anomalies miraculously cancel out in exactly 10 dimensions when string theory incorporates supersymmetry, a proposed symmetry between force-carrying bosons and matter-carrying fermions. This anomaly cancellation represents one of the most remarkable mathematical coincidences in physics, suggesting that 10-dimensional string theory might describe the actual structure of physical reality. The specific dimensional requirement of string theory is unarbitrary, but emerges from the deep mathematical structure of how strings can consistently interact and evolve. String interactions involve the joining and splitting of one-dimensional strings in high-dimensional space, creating two-dimensional surfaces called world sheets. The mathematical consistency of these world sheet dynamics requires exactly the right amount of dimensional freedom to avoid pathological behaviors. Edward Witten's work on M-theory in 1995 revealed that string theory actually represents different perspectives on a more fundamental 11-dimensional theory. M-theory unifies the 5 different consistent versions of 10-dimensional string theory by showing that they read different mathematical descriptions of the same underlying 11-dimensional physics. This 11-dimensional framework provides the most complete current understanding of how extra dimensions might be integrated into fundamental physics. The vibrating strings in these extra dimensions don't just exist. They create all the particles and forces we observe in our 3-dimensional experience. Different vibrational patterns of fundamental strings correspond to different particle types: electrons, photons, quarks, neutrinos, and even gravitons. The richness of particle physics emerges from the geometric complexity of string vibrations in higher dimensional space. The compactification of extra dimensions in string theory occurs through Calabi-Yau manifolds, complex 6-dimensional geometric shapes that provide the mathematical framework for how 6 of the 9 spatial dimensions can be curled up at every point in 3-dimensional space. The specific geometry of these Calabi-Yau manifolds determines the observable properties of particles and forces in our 3-dimensional experience. Thousands of different Calabi-Yau manifolds are mathematically possible, each corresponding to a different compactification scheme that would produce different particle masses, interaction strengths, and physical constants. This vast landscape of possible string theory vacua creates both an opportunity and a challenge. String theory might explain why physical constants have their observed values through extra-dimensional geometry, but it also suggests that many other physical realities might be possible with different compactification choices. The mathematical elegance of string theory becomes apparent when you consider how it unifies all fundamental forces through higher dimensional geometry. In our 3-dimensional experience, gravity, electromagnetism, and the strong and weak nuclear forces appear to be completely separate phenomena with different strengths and behaviors. But in 10 or 11 dimensions, these forces emerge as different aspects of string and membrane dynamics in higher dimensional space. Gravity appears weak compared to other forces because it's the only force that can propagate through all dimensions of space, including the hidden ones. While electromagnetic and nuclear forces are confined to our three-dimensional brain, lower dimensional surface embedded in higher dimensional space gravitational effects can spread through the extra dimensions, diluting gravity as apparent strength in 3 dimensions while revealing its true strength only when all dimensions are considered. The concept of brand-new scenarios, developed by physicists like Lisa Randall and Raymond Sundram, suggests that our 3-dimensional space might be a brain floating in higher dimensional space called the bulk. All matter and non-gravitational forces would be confined to the brain, while gravity could propagate through the bulk. This would explain why gravity appears so much weaker than other forces while making specific predictions about extra-dimensional physics. Recent developments in string theory have revealed additional mathematical structures that require extra dimensions. ADS-CFT correspondence, discovered by Juan Maldacena, creates a precise mathematical relationship between gravitational theories and higher dimensional anti-de Sitter space and quantum field theories on the lower dimensional boundary. This correspondence suggests deep connections between quantum mechanics and gravity that only become apparent in higher dimensional contexts. The holographic principle emerging from string theory suggests that all information contained in a volume of space can be encoded on its lower dimensional boundary. This remarkable result implies that our 3-dimensional experience might be a holographic projection of more fundamental physics occurring in higher dimensional space. The apparent solidity and 3-dimensionality of matter might be emergent phenomena arising from information processing in extra dimensions. String theory's requirement for extra dimensions isn't merely a mathematical curiosity. It makes specific testable predictions about physics at high energies. When particle accelerators reach sufficiently high collision energies, they should begin to probe the compactified extra dimensions, potentially creating signatures of higher dimensional physics through missing energy, extra-dimensional particle production, or modifications to gravitational behavior at short distances. The mathematical beauty of string theory lies in how it reduces the apparent complexity of particle physics to geometric simplicity in higher dimensions. Instead of requiring dozens of arbitrary parameters to describe particle masses and interaction strengths, string theory suggests that these properties emerge naturally from the geometry of extra dimensions. Physical complexity in 3 dimensions arises from geometric elegance in 10 or 11 dimensions. As you contemplate the mathematical necessity of extra dimensions in string theory, recognize that this represents more than abstract theoretical speculation. The mathematical consistency requirements that demand extra dimensions are the same mathematical principles that have successfully described every other aspect of fundamental physics. If string theory is correct, then extra dimensions aren't optional features of reality. They are essential components of the mathematical structure that makes physical existence possible. The strings vibrating through these hidden dimensions aren't in some distant realm. They constitute the fundamental level of your own physical existence. Every atom in your body, every photon reaching your eyes, every force holding your molecules together emerges from string dynamics in higher dimensional space that your 3-dimensional consciousness cannot directly perceive, but depends upon for its very existence. But string theory's mathematical requirements are just the beginning. We must now examine how extra dimensions could hide from direct observation through the geometric process of compactification. Chapter 3. Compactification Mechanisms. The most profound question in higher dimensional physics isn't whether extra dimensions could exist, but how they could be present everywhere around us while remaining completely invisible to direct observation. The answer lies in compactification, a geometric mechanism that allows spatial dimensions to be curled up into structures so incredibly small that they exist at every point in space, but remain below the threshold of detection by any possible measurement apparatus. Imagine you're looking at a garden hose from a great distance. The hose appears to be one-dimensional. You can only see its length stretching across your field of view. But as you move closer, you discover that the hose actually has additional dimensions, circumference and thickness that were invisible when viewed from far away. The hose is really three-dimensional, but two of those dimensions were compactified into such a small scale that they became undetectable from a distance. Extra spatial dimensions could be hidden in an analogous way at every point in three-dimensional space. The mathematical framework for compactification was first developed by Oscar Klein in 1926, building on Theodor Kaluza's five-dimensional theory of electromagnetism and gravity. Klein proposed that the fifth dimension could be curled up into a circle with a radius so small on the order of the Planck length, about 10 to 35 meters, that no conceivable experiment could detect its presence. Particles moving through ordinary space would also be moving around this tiny circular dimension, but the extra motion would be invisible to our measuring instruments. The Planck length represents a fundamental scale in physics where quantum mechanical effects and gravitational effects become equally important. At this scale, the uncertainty principle ensures that space and time themselves become uncertain and fluctuating. If extra dimensions are compactified at or below the Planck scale, then the quantum foam of space-time would mask their presence, making direct detection fundamentally impossible with any conceivable technology. Modern compactification scenarios involve far more complex geometries than Klein's simple circular dimension. Calabi-Yau manifolds named after mathematicians Eugenio Calabi and Xingtao Yau provide six-dimensional geometric structures that can be compactified at each point in three-dimensional space. These mathematical objects possess extraordinary geometric properties. They have no boundary. They exhibit complex topological features, and they can support rich internal symmetry structures that determine particle physics. The geometric complexity of Calabi-Yau manifolds is staggering. These six-dimensional spaces can contain hundreds of topological holes, twisted cycles, and intricate geometric relationships that have no analogy in three-dimensional space. The specific shape and topology of the compactified dimensions determines the fundamental properties of particles and forces that we observe in our three-dimensional experience. Each different Calabi-Yau manifold corresponds to a different possible compactification scheme, creating what string theorists call the landscape, a vast collection of possible vacuum states, each with different particle masses, interaction strengths, and physical constants. Current estimates suggest there might be 10,500 or more mathematically consistent Calabi-Yau manifolds, each representing a different way that extra dimensions could be hidden while producing different observable physics. The size of compactified dimensions doesn't have to be Planck scale. Lisa Randall and Raymond Sundram demonstrated that extra dimensions could be much larger, potentially even millimeter-sized, if they possess specific geometric properties that still keep them hidden from ordinary observation. Their warped extra dimension models show how gravity could leak into a large extra dimension while electromagnetic and nuclear forces remain confined to our three-dimensional brain. In Randall-Sundram scenarios, space itself has a curved, warped geometry in the extra dimension, similar to how a funnel has curved two-dimensional surface embedded in three-dimensional space. This warping can create apparent weakness of gravity in our three-dimensional experience, even if gravity has normal strength in the full higher-dimensional space. The extra dimension acts like a gravitational drain that dilutes gravitational effects while keeping other forces confined to three dimensions. Flux compactification represents another mechanism for hiding extra dimensions through background field configurations. Imagine electromagnetic fields or other force fields threading through the extra dimensions, creating field energy that stabilizes the size and shape of compactified dimensions. These background fluxes can wrap around topological cycles in the extra dimensions, creating quantized field configurations that determine both the compactification geometry and the resulting particle physics. The mathematical description of compactification involves complex differential geometry and topology that reveals deep connections between higher dimensional geometry and observable physics. Hodge theory, cohomology groups, and moduli spaces provide the mathematical tools for understanding how geometric properties of extra dimensions translate into particle masses, force strengths, and other measurable quantities. Brane world models suggest that our three-dimensional space is actually a lower-dimensional surface, a brane, embedded within higher-dimensional space called the bulk. All ordinary matter and non-gravitational forces are confined to the brane, while only gravity can propagate freely through the bulk dimensions. This scenario allows extra dimensions to be large while remaining invisible to electromagnetic probes that cannot escape from the three-dimensional brane. The confinement of particles to lower-dimensional branes occurs through topological and dynamical mechanisms that trap certain types of fields within subspaces of the full higher-dimensional theory. Open strings, which have endpoints, can be confined to branes because their endpoints cannot move freely through the bulk. Closed strings, including gravitons, can propagate through all dimensions, explaining why gravity has access to extra dimensions while matter particles remain trapped in three dimensions. Large extra dimension scenarios suggest that gravity could become strong at millimeter distances if extra dimensions are large enough. This would modify Newton's inverse square law of gravitation at short distances, potentially making extra-dimensional effects detectable through precision gravitational experiments. The apparent weakness of gravity compared to other forces could be explained by gravitational flux spreading through large extra dimensions instead of being confined to three dimensions. Warped product spaces provide mathematical frameworks for compactification scenarios, where different regions of space have different effective dimensionalities. Parts of higher dimensional space could be effectively three-dimensional due to geometric warping, while other regions maintain their full higher dimensional character. This creates complex spacetime architectures where dimensional structure varies depending on location and energy scale. The stability of compactified extra dimensions requires sophisticated mechanisms to prevent them from expanding back to macroscopic sizes or collapsing to zero size. Moduli stabilization involves background fluxes, quantum corrections, and non-perturbative effects that fix the size and shape of extra dimensions at specific values. Without stabilization mechanisms, compactified dimensions would be dynamical rather than static, potentially leading to observable time variation of physical constants. Orbifold compactification provides another approach to dimensional hiding through discrete symmetries that identify different points in extra dimensions. Instead of smooth compactification on curved manifolds, orbifolds involve flat extra dimensions with specific boundary conditions that effectively reduce their size and complexity. This approach often leads to more tractable mathematical calculations while still achieving dimensional hiding. The process of dimensional transmutation shows how physics at different energy scales can appear to involve different effective numbers of dimensions. At low energies, where wavelengths are large compared to compactification scales, physics appears three-dimensional because extra dimensions are too small to resolve. At high energies, where wavelengths become comparable to compactification scales, the full higher dimensional structure becomes relevant for particle interactions and force behaviors. Kaluza-Klein modes represent the signature of extra dimensions in particle physics. When particles move through compactified extra dimensions, Their momentum in the hidden dimensions appears as quantized energy levels, discrete mass states that correspond to different vibrational modes in the extra dimensions. Detecting these Kaluza-Klein particle towers in accelerator experiments would provide direct evidence for extra-dimensional physics. The phenomenology of compactified extra dimensions creates specific predictions for deviations from three-dimensional physics at high energies or short distances. Gravitational experiments at sub-millimeter scales, precision tests of Coulomb's law, and high-energy particle collisions all provide windows into potential extra-dimensional effects that could reveal the presence of hidden spatial dimensions. As you consider the mechanisms that could hide extra dimensions from your direct perception, recognize that compactification represents one of the most elegant solutions to apparent contradictions between mathematical theory and observational reality. The same space you're reoccupying right now could contain 6 additional spatial dimensions, curled up so tightly that every point around you possesses geometric complexity that exceeds your three-dimensional imagination. The mathematics of compactification aren't just abstract geometry. They provide specific mechanisms that could explain some of the deepest mysteries in physics through the hidden complexity of higher dimensional space. But mathematical possibility is just the first step toward understanding whether extra dimensions actually exist. We must now examine the experimental evidence that hints at their reality. Chapter 4. Experimental hints while extra dimensions remain hidden from direct observation. Cutting-edge experiments at particle accelerators, gravitational laboratories, and astronomical observatories are beginning to detect subtle signatures that could provide the first evidence for spatial dimensions beyond the 3 we directly experience. These experimental hints don't prove extra dimensions exist, but they reveal anomalies and patterns that extra-dimensional physics could elegantly explain. The Large Hadron Collider at CERN represents humanity as most powerful probe into the high-energy realm where extra-dimensional effects should become detectable. When protons collide at energies approaching 14 TeV, the tremendous concentration of energy in tiny volumes could potentially create particles that escape into extra dimensions or produce Kaluza-Klein excitations, heavier versions of ordinary particles that correspond to momentum in hidden dimensions. One of the most intriguing signatures detected at the LHC involves missing energy events, where the total energy and momentum before collision doesn't equal the detectable energy and momentum after collision. While some missing energy can be explained by neutrinos escaping detection, excess missing energy beyond standard model predictions could indicate particles escaping into extra dimensions where our detectors cannot follow them. The ATLAS and CMS detectors at the LHC have observed missing energy signatures in high-energy collisions that exceed standard model expectations in specific energy regimes. While these anomalies could have conventional explanations, extra-dimensional models provide natural explanations for missing energy through graviton production and escape into bulk dimensions that surround our three-dimensional brain. Gravitational experiments at sub-millimeter scales have tested Newton's inverse square law with extraordinary precision, searching for deviations that could indicate gravitational leakage into large extra dimensions. The work of Eric Adelberger, Jens Gunlech, and their collaborators at the University of Washington has probed gravitational behavior down to distances of about 50 micrometers, finding no deviations from Einstein's general relativity, but placing important constraints on extra-dimensional scenarios. The ETH-WASH group as torsion balance experiments represent the most precise tests of gravitational behavior at short distances ever conducted. These experiments suspend test masses on torsion fibers and measure gravitational forces with sensitivities approaching 10 to 17 newtons. If extra dimensions are larger than about 100 micrometers, these experiments should detect modifications to gravitational strength that would indicate gravitational flux spreading through hidden dimensions. Astronomical observations provide another window into potential extra-dimensional effects through gravitational phenomena that might involve higher-dimensional physics. The rotation curves of spiral galaxies, the dynamics of galaxy clusters, and gravitational lensing observations reveal gravitational effects that exceed what can be explained by visible matter alone. While dark matter provides the conventional explanation, some extra-dimensional models offer alternative explanations through modified gravitational behavior in higher-dimensional space. The Pioneer anomaly, observed in the trajectories of Pioneer 10 and 11 spacecraft as they traveled to the outer solar system, showed unexplained acceleration toward the Sun that couldn't be accounted for by known gravitational sources. While conventional explanations involving thermal recoil forces have now been accepted, the anomaly initially prompted investigation of modified gravity theories and extra-dimensional scenarios that could explain anomalous gravitational behavior at large distances. Dark energy observations through Type Ia supernova, cosmic microwave background measurements, and baryon acoustic oscillation surveys reveal that cosmic expansion is accelerating due to unknown energy density that comprises about 68% of the universe's total energy content. Some extra-dimensional models propose that dark energy could emerge from the geometry and dynamics of hidden dimensions, providing potential explanations for cosmic acceleration through higher-dimensional physics. The hierarchy problem in particle physics, why gravity is so much weaker than other fundamental forces, receives natural explanation in some extra-dimensional scenarios. If gravity can propagate through large extra dimensions while other forces remain confined to 3 dimensions, then gravitational flux would be diluted through the higher dimensional volume, making gravity appear weak in 3 dimensions while maintaining normal strength in the full higher dimensional space. 1G2 experiments at Fermilab have measured the anomalous magnetic moment of muons with extraordinary precision, revealing small discrepancies between experimental values and standard model predictions. While these anomalies might have conventional explanations through quantum corrections, some extra-dimensional models predict specific contributions to muon magnetic moments through virtual particle loops that involve Kaluza-Klein excitations in hidden dimensions. Neutrino oscillation experiments have revealed that neutrinos have small but non-zero masses and can change between different types during propagation. Some theoretical models suggest that neutrino masses could arise through coupling to extra dimensions, with right-handed neutrino states propagating in the bulk, while left-handed states remain confined to our 3-dimensional brain. This could explain both neutrino masses and the observed pattern of neutrino mixing angles. The Mini-Buoni experiment at Fermilab has observed anomalous neutrino interactions that exceed standard model expectations, potentially indicating the existence of sterile neutrinos, hypothetical particles, that interact only through gravitational forces and could propagate in extra dimensions. While these results remain controversial and require confirmation, they hint at possible connections between neutrino physics and higher dimensional scenarios. Cosmic ray experiments detect ultra-high energy particles from space with energies exceeding 1020 electron volts, energy so high that they approach the theoretical cutoff imposed by interactions with cosmic microwave background radiation. Some extra-dimensional models predict that these extreme energies could be achieved through particle acceleration processes involving higher dimensional physics or through the decay of massive Kaluza-Klein particles in the bulk. String phenomenology models make specific predictions for particle masses, interaction strengths, and coupling constants based on extra-dimensional compactification geometries. The Large Hadron Collider's precision measurements of Higgs boson properties, top quark masses, and gauge coupling evolution provide increasingly stringent tests of these predictions. Any deviations from standard model expectations in these precision measurements could indicate extra-dimensional contributions to particle physics. Gravitational wave detectors like LIGO and Virgo have opened a new window into strong field gravitational physics, where extra-dimensional effects could potentially become observable. If extra dimensions exist, gravitational waves could potentially propagate through the bulk dimensions in addition to our three-dimensional brain, creating specific signatures in gravitational wave polarizations and propagation speeds that could be detected with sufficient sensitivity. The European Space Agency's Lisa mission, scheduled for the 2030s, will detect gravitational waves in space with unprecedented sensitivity and precision. Lisa's measurements could potentially reveal deviations from Einstein's general relativity that might indicate extra-dimensional modifications to gravitational wave propagation through higher dimensional space. Tabletop experiments searching for new forces and particles provide increasingly sensitive probes of potential extra-dimensional physics. Axion searches, dark photon experiments, and tests of equivalence principle violations all could potentially detect signatures of extra dimensions through new particles or forces that couple ordinary matter to hidden dimensional sectors. The anomalous magnetic moment of the electron, measured with parts per trillion precision, provides another stringent test of extra-dimensional contributions to particle physics. While current measurements agree with standard model predictions to extraordinary precision, future improvements in experimental sensitivity could potentially reveal tiny extra-dimensional contributions that would indicate the presence of hidden spatial dimensions. Precision tests of quantum electrodynamics through measurements of the fine structure constant, electron G-factor, and atomic transition frequencies provide indirect but extremely sensitive probes of potential extra-dimensional physics. Any time variation in fundamental constants could indicate moduli fields associated with extra-dimensional compactification, while precision measurements of physical constants provide tests of extra-dimensional model predictions. The ongoing search for supersymmetric particles at the LHC could reveal connections to extra-dimensional physics if supersymmetry is implemented through higher dimensional theories. Many string theory models predict specific patterns of supersymmetric particle masses and interactions based on extra-dimensional compactification details, creating connections between supersymmetry searches and extra-dimensional phenomenology. As you contemplate these experimental hints and ongoing searches, recognize that we may be living at a historic moment when humanity first detects evidence for spatial dimensions beyond direct experience. The experiments probing extra-dimensional physics operate at the cutting edge of technological capability, pushing measurement precision to levels that could reveal the hidden dimensional structure of reality itself. Each experimental anomaly or precision measurement provides another piece of the puzzle that could eventually reveal whether our three-dimensional experience represents the totality of spatial reality or merely the observable surface of a vastly more complex, higher-dimensional universe. But experimental hints alone cannot capture the full implications of what extra dimensions would mean. We must explore the theoretical possibility that entire parallel universes could exist in the space right next to us. Chapter 5. Parallel Universes. If extra spatial dimensions exist, they create the mind-bending possibility that entire parallel universes could be located just millimeters away from you in higher dimensional space, completely invisible and inaccessible from our three-dimensional perspective, but existing in the same physical location through separation in dimensions we cannot perceive. This isn't science fiction. It is a serious theoretical possibility that emerges directly from the mathematics of higher dimensional physics. The concept of parallel universes in extra dimensions differs fundamentally from parallel universes in quantum mechanics or cosmology. Instead of alternative realities created by quantum measurement or cosmic inflation, extra-dimensional parallel universes exist in the same space-time location, but are separated by displacement in spatial dimensions we cannot access. These universes could be closer to you then the screen you're rereading separated by distances measured not in meters, but in movements through fourth, fifth, or sixth spatial dimensions. Brain world scenarios provide the theoretical framework for understanding how parallel universes could exist in extra dimensions. If our three-dimensional space is a brain, a lower dimensional surface embedded in higher dimensional space, then other three-dimensional brains could exist elsewhere in the same higher dimensional bulk space. Each brain would contain its own matter, energy, forces, and potentially life, but they would be completely isolated from each other except through gravitational effects that can propagate through the bulk. The mathematical description of parallel brains in higher dimensional space reveals extraordinary possibilities. Two three-dimensional universes could be separated by a distance of just 1 millimeter in a fourth spatial dimension while being completely inaccessible to each other. No amount of movement within either three-dimensional space could ever bring the universes into contact, because the separation exists in a spatial direction that neither universe can access. Lisa Randall and Raymond Sundram's work on warped extra dimensions demonstrates how parallel brains could exist at different positions in a curved fifth dimension, each experiencing different effective gravitational strengths and physical constants due to their position in the warped geometry. Our observable universe could be one brain in a higher dimensional space that contains numerous other brain universes, each with potentially different physics. The Arkany-Hammond, Dimopoulos, and Valley, a DD model proposes that gravity appears weak in our universe because gravitational effects are diluted through large extra dimensions that could contain other brain universes. If extra dimensions are large, potentially millimeter-sized, then parallel universes separated by small distances in these dimensions could exist without ever being detectable through electromagnetic or nuclear interactions. String theory as landscape of possible compactifications creates a vast multiverse where different regions of higher dimensional space could have different compactified dimensions, leading to different effective physics in each region. Some areas of the higher dimensional space could support universe like ours, while other regions could have entirely different particle physics, force strengths, or even different numbers of effective spatial dimensions. The collision of parallel brains in higher dimensional space could provide a mechanism for the Big Bang and cosmic inflation. Ekpyrotic scenarios propose that our universe's birth resulted from the collision of two brains in extra dimensions, with the collision energy creating the hot, dense initial conditions that led to the expansion and evolution of our observable cosmos. Other brain collisions throughout higher dimensional space could be creating other universes continuously. Mirror matter theory suggests that our universe could have a parallel partner universe containing mirror versions of all particles and forces, existing in the same three-dimensional space, but interacting only very weakly with ordinary matter. While not strictly extra-dimensional, these theories demonstrate how parallel realities could coexist in ways that make them almost entirely invisible to direct observation, while still having subtle physical effects. The possibility of communication between parallel brains depends on which forces and particles can propagate through the bulk dimensions. If only gravity can travel between brains, then parallel universes would be nearly impossible to detect except through extremely subtle gravitational effects. If other forces or particles can travel through extra dimensions, then more direct communication or detection mechanisms might be possible. Kaluza-Klein particles provide potential messengers between parallel brains by carrying information through extra dimensions. High-energy particle collisions could potentially create massive Kaluza-Klein excitations that travel through the bulk and decay on other brains, providing a mechanism for energy and information transfer between parallel universes. Such effects would be extremely subtle and difficult to detect with current technology. The anthropic principle gains new significance in extra-dimensional parallel universe scenarios. If countless parallel universes exist with different physical constants and force strengths, then the apparent fine-tuning of physics for the existence of complex structures in life could be explained by selection effects. We necessarily observe a universe compatible with our existence, while countless other universes with incompatible physics exist unobserved in extra dimensions. Dark matter could potentially originate from parallel branes in extra dimensions if particles from other universes can exert gravitational effects in our space while remaining invisible to electromagnetic interactions. This krypton dark matter scenario suggests that what we interpret as dark matter could actually be ordinary matter existing on parallel branes that interact with our universe only through gravity. The hierarchy between the Planck scale and the electroweak scale, why gravity appears weak compared to other forces, could be explained by parallel brane scenarios where the fundamental scale of physics is much lower than the apparent Planck scale in 4 dimensions. If extra dimensions are large and contain parallel universes, then the true fundamental scale could be as low as 1 TeV, making extra-dimensional physics potentially accessible to current particle accelerators. Parallel universe scenarios in extra dimensions create potential explanations for cosmic mysteries like dark energy. The acceleration of cosmic expansion could result from interactions between our brane universe and other branes in extra dimensions, with the attractive or repulsive forces between branes manifesting as effective dark energy that drives accelerated expansion in our 3-dimensional space. The stability of parallel branes requires sophisticated physics to prevent them from colliding and destroying each other. Moduli stabilization mechanisms must maintain fixed separations between branes in extra dimensions, while background fluxes and geometric properties of the higher dimensional space must conspire to create stable equilibrium configurations that allow parallel universes to coexist indefinitely. Cosmological evolution in parallel brane scenarios involves complex dynamics where different universes can influence each other as expansion rates, temperature histories, and structure formation processes through gravitational effects that propagate through the bulk. This could lead to synchronized evolution phases or complex feedback effects between parallel cosmic histories. The possibility of traversing between parallel universes depends on the physics of higher dimensional space and whether stable passages or tunnels could exist between different branes. Wormhole-like connections through extra dimensions could theoretically allow travel between parallel universes, but such connections would likely require exotic matter or energy configurations that may be physically impossible to create or maintain. Observational signatures of parallel universes could include anomalous gravitational effects, missing energy in particle collisions, modifications to cosmic expansion histories, or statistical correlations in cosmic microwave background fluctuations that indicate interactions with other cosmic domains. However, these signatures would likely be extremely subtle and difficult to distinguish from other exotic physics. The philosophical implications of parallel universes in extra dimensions are profound. If countless other realities exist just millimeters away in directions we cannot access, then questions about uniqueness, specialness, and the meaning of existence take on entirely new dimensions. The universe would be not a single cosmic domain, but an incomprehensibly vast collection of parallel realities, each as real and complex as our own. Parallel universes in extra dimensions also raise questions about identity and consciousness. If quantum mechanics allows for multiple parallel states and extra dimensions allow for multiple parallel universes, then conscious experience might represent just one thread in an infinite tapestry of parallel experiences, occurring simultaneously across higher dimensional space. As you contemplate the possibility that parallel universes could exist just outside your 3-dimensional perception, consider that every point around you could be a location where other entire realities intersect with your experience while remaining completely hidden. The space you're occupying could be shared by countless other forms of matter, energy, and potentially consciousness that exist in dimensions your senses cannot detect. But parallel universes represent just one possibility that emerges from extra-dimensional physics. We must now explore how the apparent weakness of gravity compared to other fundamental forces could provide the most compelling evidence that extra dimensions exist. Chapter 6: Gravity's Great Escape. Gravity presents one of the most mysterious puzzles in fundamental physics. It is incomprehensibly weaker than the other fundamental forces. The electromagnetic force that holds atoms together is about 1,036 times stronger than the gravitational force that holds you to Earth. This enormous hierarchy between force strengths has puzzled physicists for decades, but extra-dimensional physics offers an elegant solution. Gravity appears weak because it is the only force that can escape into hidden dimensions, diluting its strength in our three-dimensional experience while maintaining normal strength in the full higher dimensional space. Consider the scale of gravity's weakness compared to other forces. The electromagnetic repulsion between two protons is about 1036 times stronger than their gravitational attraction. If electromagnetic and gravitational forces had equal strength, your body would not be held together by molecular bonds. It would either collapse into a black hole or be torn apart by electromagnetic repulsion. The weakness of gravity is essential for the existence of complex matter structures, but it's also completely mysterious from a three-dimensional perspective. The standard model of particle physics describes electromagnetic, weak, and strong nuclear forces with extraordinary precision, but it cannot explain why these forces are so much stronger than gravity. All attempts to unify gravity with other forces in three-dimensional theories encounter the hierarchy problem, the unexplained enormous difference in force strengths that seems to require inexplicable fine-tuning of physical constants to achieve the observed values. Extra-dimensional scenarios provide a natural solution to the hierarchy problem by proposing that gravity is not inherently weak, but appears weak because gravitational effects are diluted through higher dimensional space, while electromagnetic and nuclear forces remain confined to our three-dimensional brain. Gravity can propagate freely through all dimensions of space, including hidden dimensions that we cannot directly perceive. The mathematical framework for gravitational dilution through extra dimensions was first developed by Nima Arkani-Hamed, Savas Dimopoulos, and Giovanni in their ADD model. They demonstrated that if extra dimensions are sufficiently large, potentially as large as millimeters, then gravitational flux spreading through the higher dimensional volume would naturally explain why gravity appears weak compared to forces confined to three dimensions. The inverse square law of gravity in three dimensions becomes an inverse higher power law when extra dimensions are considered. Lisa Randall and Raymond Sundram developed an alternative approach through warped extra dimensions, where our three-dimensional space exists as a brane in a curved five-dimensional space-time. In their model, gravity can have normal strength on one brane while appearing much weaker on our brain due to geometric effects of the warped fifth dimension. This provides another mechanism for explaining gravitational weakness through extra-dimensional geometry rather than fundamental force weakness. The RS1 model places our visible universe on a TeV brane where the effective Planck scale is much lower than the apparent Planck scale in 4 dimensions, potentially making quantum gravitational effects observable at energies accessible to particle accelerators. The RS2 model extends space infinitely in the extra dimension, creating a scenario where gravity can have normal strength while appearing weak in our three-dimensional experience due to the infinite extra-dimensional volume. Gravitational experiments at sub-millimeter distances provide the most direct tests of extra-dimensional gravitational effects. If gravity spreads through large extra dimensions, then Newton's inverse square law should be modified at distances comparable to the size of extra dimensions. Precision measurements of gravitational forces at microscopic scales could directly detect the transition from three-dimensional to higher-dimensional gravitational behavior. The Edwash Group's torsion balance experiments have tested gravitational behavior down to distances of about 50 micrometers, finding no deviations from Einstein's general relativity, but placing important constraints on extra-dimensional scenarios. These experiments are sensitive enough to detect gravitational modifications from millimeter-sized extra dimensions, ruling out the simplest versions of large extra-dimension scenarios while leaving room for more complex geometric possibilities. Modified gravity experiments using atomic interferometry and other precision techniques continue to push the sensitivity limits for detecting extra-dimensional gravitational effects. Future experiments could potentially detect gravitational modifications at even shorter distances, probing the microscopic regime where extra-dimensional effects should become observable if large extra dimensions exist. The weakness of gravity compared to other forces becomes even more mysterious when viewed from the perspective of quantum field theory. The natural expectation is that all forces should have comparable strengths at the Planck scale, where quantum mechanics and gravity become equally important. The fact that gravity appears weak at all observed energy scales suggests either incredible fine-tuning or new physics that explains the hierarchy. String theory provides additional insight into gravitational weakness through the relationship between closed and open strings. Gravitons correspond to closed strings that can propagate freely through all dimensions of space, while particles corresponding to other forces arise from open strings with endpoints confined to branes. This fundamental difference between closed and open string dynamics provides a natural explanation for why gravity alone can access extra dimensions. The ADS-CFT correspondence demonstrates precise mathematical relationships between gravitational theories in higher-dimensional anti-de Sitter space and quantum field theories on lower-dimensional boundaries. This holographic duality suggests that gravitational physics in higher dimensions can be exactly equivalent to non-gravitational physics in lower dimensions, providing new perspectives on how gravitational effects might be distributed across different dimensional sectors. Phenomenological consequences of gravity's escape into extra dimensions include specific predictions for high-energy physics at particle accelerators. If extra dimensions are large enough, then particle collisions at high energies could create virtual gravitons that escape into the bulk, appearing as missing energy in detector systems. The rate of graviton production would depend on the number and size of extra dimensions, creating testable predictions for collider experiments. Black hole production at particle accelerators becomes possible in scenarios with large extra dimensions because the effective Planck scale could be much lower than the apparent Planck scale in 4 dimensions. If the fundamental scale of gravity is at the TeV scale rather than the Planck scale, then high-energy particle collisions could potentially create microscopic black holes that would immediately evaporate through Hawking radiation, providing dramatic signatures of extra-dimensional physics. Cosmological implications of gravitational escape include modifications to the expansion history of the universe, changes in structure formation processes, and potential explanations for dark energy through extra-dimensional effects. If gravity can leak into extra dimensions during cosmic evolution, this could affect the relationship between matter density and expansion rate, potentially explaining cosmic acceleration without requiring mysterious dark energy. Gravitational wave astronomy provides new opportunities to test extra-dimensional modifications of gravity through precision measurements of gravitational wave propagation speeds, polarizations, and interaction effects. If gravity spreads through extra dimensions, gravitational waves might propagate differently than Einstein's general relativity predicts, creating observable signatures in gravitational wave observations from merging black holes and neutron stars. The Lisa space-based gravitational wave detector, scheduled for launch in the 2030s, will provide unprecedented sensitivity for detecting deviations from general relativity that could indicate extra-dimensional modifications of gravitational physics. LIS's precision could potentially reveal extra-dimensional signatures through subtle modifications to gravitational wave propagation properties. Theoretical developments in extra-dimensional gravity continue to reveal new possibilities for understanding gravitational weakness through higher-dimensional physics. DGP gravity models, cascading gravity scenarios, and other exotic gravitational theories explore different ways that gravity could be modified by extra-dimensional effects while remaining consistent with current experimental constraints. The hierarchy problem extends beyond gravity to other aspects of particle physics, including the enormous difference between the electroweak scale and the Planck scale. Extra-dimensional solutions to these hierarchy problems suggest that apparent energy scale separations in particle physics could be explained by geometric effects in higher dimensional space rather than fundamental scale separations. Gauge gravity duality emerging from string theory reveals deep connections between gravitational physics in higher dimensions and gauge field theories in lower dimensions. These dualities suggest that gravitational physics might be fundamentally holographic, with gravitational degrees of freedom in extra dimensions being dual to gauge field degrees of freedom in fewer dimensions. As you consider the possibility that gravity's weakness results from its escape into hidden dimensions, recognize that this would fundamentally transform our understanding of space and physical law. Every gravitational effect you experience, your weight, tidal forces, orbital motion, would represent just a three-dimensional shadow of gravitational physics occurring in higher dimensional space that your senses cannot access. The fact that you can lift your arm against Earth as gravitational field using just the electromagnetic forces generated by your muscles demonstrates gravity as remarkable weakness. If extra dimensions exist, this everyday experience reflects the dilution of gravitational strength through higher dimensional space, making gravity appear weak compared to forces confined to 3 dimensions, while revealing the hidden complexity of spatial reality. But gravitational weakness is just one piece of evidence pointing toward extra dimensions. We must now examine how the mathematics of higher dimensions reveal geometric possibilities that exceed our 3-dimensional imagination. Chapter 7. Higher Dimensional Mathematics. The mathematics of spaces with more than 3 dimensions reveals geometric possibilities that transcend anything imaginable within our 3-dimensional experience, creating frameworks for understanding how reality could extend through spatial dimensions that remain forever beyond direct visualization, while being precisely describable through mathematical tools that capture their essential properties and relationships. Our 3-dimensional intuition fails completely when attempting to visualize 4-dimensional space, let alone the 6 or 7 extra dimensions that string theory requires. However, mathematical analysis reveals that higher dimensional spaces possess well-defined geometric properties that can be calculated, measured, and understood even when they cannot be directly visualized. The mathematics provides access to higher dimensional reality that our visual imagination cannot achieve. Consider a simple example of higher dimensional geometry, a 4-dimensional hypercube, also called a tesseract. While you cannot visualize this object directly, its mathematical properties are completely well-defined. A tesseract has 16 vertices, 32 edges, 24 square faces, and 8 cubic cells. It can be constructed mathematically by extending a 3-dimensional cube into the 4th dimension, creating an object that encloses 4-dimensional volume, just as a cube encloses 3-dimensional volume. The rotation of objects in 4 dimensions creates phenomena impossible in 3-dimensional space. A 3-dimensional object can be completely turned inside out in 4 dimensions without cutting, stretching, or breaking any part of the object. A right-handed glove can be transformed into a left-handed glove by rotating it through the fourth dimension. Knots can be untied by moving them through four-dimensional space, demonstrating how extra dimensions provide freedoms unavailable in lower dimensions. Hypersurfaces in higher dimensions create geometric structures of extraordinary complexity and beauty. Calabi-Yau manifolds, the six-dimensional spaces that provide frameworks for extra-dimensional compactification in string theory, possess geometric properties that have no analog in familiar three-dimensional space. These manifolds can have hundreds of topological holes, complex symmetry groups, and intricate relationships between different geometric cycles that determine particle physics properties. The mathematical description of Calabi-Yau manifolds requires sophisticated tools from algebraic geometry, differential geometry, and topology. Cohomology groups classify the different types of topological holes in these spaces. Hodge numbers count specific geometric structures. Moduli spaces describe how the shapes of these manifolds can be continuously deformed while maintaining their essential mathematical properties. Ricci flat metrics on Calabi-Yau manifolds ensure that these six-dimensional spaces have zero curvature in specific mathematical senses, making them suitable for string theory compactification. The mathematical requirement for Ricci flatness constrains the possible geometries of extra dimensions, creating deep connections between pure mathematics and fundamental physics that neither field anticipated when these mathematical structures were first discovered. Mirror symmetry in mathematics reveals that apparently different Calabi-Yau manifolds can be equivalent for string theory purposes, related by transformations that exchange geometric and topological properties. This mathematical duality suggests that the geometry of extra dimensions might not be unique. Different geometric descriptions could correspond to the same physical reality, revealing hidden symmetries in higher dimensional space. The classification of Calabi-Yau manifolds remains an active area of mathematical research with profound implications for physics. Current estimates suggest there might be hundreds of thousands or even millions of topologically distinct Calabi-Yau threefolds, three complex dimensional, or six real dimensional manifolds, each corresponding to different possible compactification schemes that would produce different particle physics and cosmological constants. Exceptional groups in mathematics provide symmetry structures that appear in higher dimensional theories but have no natural realization in three-dimensional space. E6, E7, and E8 exceptional Lie groups describe symmetries that can only be fully realized in spaces with many dimensions, suggesting that the mathematical structures underlying fundamental physics naturally require higher dimensional frameworks for their complete expression. Fiber bundles in gauge theory in higher dimensions reveal how forces and interactions can be understood as geometric phenomena in extended space. Yang-Mills theory in higher dimensions provides frameworks for unifying different forces through higher dimensional geometry, where apparently different interactions become different aspects of geometric curvature in extended space. Spinors in higher dimensions describe fundamental fermions through mathematical objects that transform under rotations in ways that have no three-dimensional analog. The representation theory of rotation groups in higher dimensions requires mathematical structures like quaternions, octonions, and more exotic algebraic systems that capture essential properties of higher dimensional geometry. Hopf fibrations demonstrate how higher dimensional spheres can be constructed as fiber bundles over lower dimensional spheres, creating geometric structures where every point in a lower dimensional base space corresponds to an entire sphere in the higher dimensional total space. These constructions reveal how complex geometric relationships emerge naturally in higher dimensions. Polytopes in higher dimensions, generalizations of polygons and polyhedra to arbitrary dimensions, exhibit geometric properties that become increasingly rich and complex as dimension increases. The 600 cell in 4 dimensions has 600 tetrahedral faces and demonstrates the extraordinary geometric complexity possible in higher dimensional spaces. Non-commutative geometry provides mathematical frameworks for understanding spaces where coordinates do not commute, where the order of measurements matters in fundamental ways. This mathematical approach, developed by Alan Kahns and others, suggests that extra dimensions might have non-commutative geometric properties that differ radically from ordinary spatial geometry. Supersymmetry mathematics requires spaces where ordinary coordinates are supplemented by anti-commuting fermionic coordinates that describe supersymmetric partners of ordinary particles. Superspace contains both bosonic dimensions corresponding to ordinary spacetime and fermionic dimensions that have no classical analog but are essential for describing supersymmetric field theories. Twistor theory, developed by Roger Penrose, provides alternative mathematical frameworks for describing 4-dimensional spacetime through complex, projective spaces that reveal hidden symmetries and structures. Twistor methods demonstrate how higher-dimensional complex spaces can provide elegant descriptions of physics in lower-dimensional real spaces. Donaldson theory and Seeberg-Witten invariance provide mathematical tools for classifying 4-dimensional manifolds and understanding their geometric properties. These mathematical developments have revealed that 4 dimensions occupy a special place in geometry. Many theorems that are true in all other dimensions fail specifically in 4 dimensions, suggesting that 4-dimensional space has unique geometric properties. Characteristic classes and K-theory provide mathematical frameworks for understanding topological properties of higher dimensional spaces that remain invariant under continuous deformations. These topological invariants classify different types of geometric structures and provide constraints on possible physical theories that can be defined on higher dimensional spaces. Differential forms and the RAM cohomology in higher dimensions provide tools for integrating over submanifolds and understanding the global geometric properties of extended spaces. The mathematics of forms reveals how higher dimensional spaces can support rich geometric structures like fluxes, monopoles, and instantons that have profound physical implications. Matroid theory and oriented matroid theory provide combinatorial approaches to higher dimensional geometry that reveal discrete structures underlying continuous geometric spaces. These mathematical frameworks show how complex geometric relationships can be encoded in simpler combinatorial data while preserving essential structural information. Category theory provides abstract mathematical frameworks for understanding relationships between different geometric structures and mathematical objects. Higher category theory, developed by mathematicians like John Baez and others, reveals deep connections between geometry, algebra, and logic that become particularly rich in higher dimensional contexts. Homotopy theory studies properties of spaces that are preserved under continuous deformations, revealing topological invariants that classify different types of geometric structures. Higher homotopy groups provide information about higher dimensional holes and loops that cannot be continuously shrunk to points, characterizing essential features of higher dimensional topology. As you contemplate these mathematical structures, recognize that they represent more than abstract intellectual constructs. If extra dimensions exist, then these mathematical frameworks describe the actual geometric properties of the space you're occupying right now. The points around you could possess 6-dimensional, Calabi-Yau, fiber structures whose topological properties determine why electrons have the masses they do and why forces have the strengths you observe. The mathematical richness of higher dimensional geometry suggests that reality could be far more complex and beautiful than 3-dimensional experience reveals. Every point in space could contain geometric structures of extraordinary sophistication, fiber bundles, topological cycles, symmetry groups, and metric configurations that require the most advanced mathematics to describe. that fundamentally shape every physical process occurring around you. But mathematical possibility is just the foundation for understanding physical reality. We must now explore the specific mechanisms through which higher dimensional geometry could determine the properties of particles and forces that we observe in our three-dimensional experience. Chapter 8. Dimensional Determination. The geometry of extra dimensions doesn't just provide abstract mathematical frameworks for physics. It actively determines the fundamental properties of matter and energy that we observe in three-dimensional space. Particle masses, force strengths, interaction patterns, and even the number of particle generations all emerge from the specific geometric configuration of hidden dimensions, making extra-dimensional geometry the hidden engine that drives all observable physics. The relationship between extra-dimensional geometry and particle properties operates through Kaluza-Klein theory, which demonstrates how motion through compactified dimensions appears as mass and charge in lower dimensional space. When a particle moves through a circular extra dimension, its momentum in the hidden dimension contributes to its energy in ways that appear as intrinsic mass from a three-dimensional perspective. Different momentum states in extra dimensions correspond to different particle masses. String theory takes this relationship to its logical conclusion by proposing that all particles are vibrating strings in higher dimensional space. The different vibrational modes of strings correspond to different particle types, with the vibration patterns determined by the geometry of the space through which the strings move. The electronic, the photon, quarks, neutrinos, and all other fundamental particles represent different geometric harmonics of string vibrations in extra-dimensional space. Calabi-Yau compactification provides the mathematical framework for understanding how six-dimensional geometric shapes determine three-dimensional particle physics. The topology of a Calabi-Yau manifold, its number of holes, cycles, and geometric relationships directly determines how many generations of particles exist, what their masses are, and how strongly they interact with each other through different forces. The number of generations of fundamental particles, 3 generations each of quarks and leptons, could be determined by the number of 3 cycles in the Calabi-Yau manifold used for compactification. Each 3 cycles supports specific types of matter fields, and the intersection patterns of different cycles determine the Yukawa couplings that generate particle masses and mixing angles through interactions with Higgs fields. Flux compactification adds background electromagnetic and other fields threading through the extra dimensions, creating additional mechanisms for determining particle properties through geometric effects. Different flux configurations can stabilize extra dimensions at specific sizes while generating different patterns of symmetry, breaking that determine which particles remain massless and which acquire masses through geometric mechanisms. The hierarchy of particle masses, why the top quark is about 350,000 times more massive than the electron, could emerge from the exponentially varying volumes of different geometric cycles in warped extra-dimensional spaces. Particles localized near different points in extra-dimensional space would experience dramatically different effective couplings to Higgs fields, naturally generating the observed hierarchy of particle masses through geometric effects. Gauge coupling unification, observed in supersymmetric theories, receives natural explanation through extra-dimensional scenarios where different gauge forces have access to different portions of higher dimensional space. The apparent convergence of electromagnetic, weak, and strong coupling constants at high energies could result from these forces becoming unified aspects of higher dimensional geometry at energy scales where extra dimensions become directly accessible. Neutrino masses present particular puzzles that extra-dimensional physics could solve through seesaw mechanisms, where right-handed neutrinos propagate in the bulk, while left-handed neutrinos remain confined to our three-dimensional brain. The tiny masses of observed neutrinos could result from their weak coupling to heavy right-handed partners existing in extra-dimensional space. The fine structure constant, the dimensionless number that determines electromagnetic interaction, strength, could be determined by the geometry of compactified dimensions through mechanisms that relate the size and shape of extra dimensions to the strength of gauge couplings. Different Calabi-Yau manifolds would produce different values of fundamental constants through their distinct geometric properties. Dark matter candidates emerge naturally from extra-dimensional scenarios through Kaluza-Klein particles, massive excited states corresponding to momentum in compactified dimensions. The lightest Kaluza-Klein particle in many models is stable and interacts only weakly with ordinary matter, making it an ideal dark matter candidate whose mass and interaction properties are determined by extra-dimensional geometry. CP violation, the slight asymmetry between matter and antimatter, could arise from complex phases in the geometry of extra dimensions. Calabi-Yau manifolds can support complex geometric structures whose phases determine the complex couplings in particle interactions, potentially explaining the observed pattern of CP violation through higher dimensional geometric effects. The cosmological constant problem. Why vacuum energy appears to be 120 orders of magnitude smaller than naive quantum field theory predictions could be solved through extra-dimensional mechanisms where vacuum energy is partially cancelled by contributions from hidden dimensions, or where the effective cosmological constant emerges from higher dimensional geometric properties rather than quantum field theory calculations. Supersymmetry breaking, required to explain why supersymmetric particle partners haven't been observed at current energy scales, could occur through geometric effects in extra dimensions where different regions of higher dimensional space break supersymmetry through flux configurations, geometric curvature, or topological effects that communicate supersymmetry breaking to our three-dimensional brain. The standard model gauge group SU 3 times SU 2 times U1 could emerge from the breaking of larger gauge symmetries through compactification on manifolds with specific geometric properties. Grand unified theories become natural in extra-dimensional frameworks where unified gauge groups are broken by geometric effects rather than spontaneous symmetry breaking through scalar field mechanisms. Proton decay rates depend sensitively on the details of grand unification and could be determined by the geometry of extra dimensions through the masses and couplings of exotic particles that mediate proton decay. Different compactification schemes predict different proton lifetimes, making proton decay experiments potential tests of specific extra-dimensional models. The theta angle in QCD, a parameter that determines the strength of CP violation in strong interactions, could be determined by geometric phases in extra-dimensional compactification. The observed smallness of the theta angle, which appears to require fine-tuning in four-dimensional theories, could be explained naturally through geometric selection effects in higher-dimensional theories. Flavor physics, the pattern of quark and lepton mixing angles and mass ratios, could be determined by the intersection properties of different geometric cycles in Calabi-Yau manifolds. The seemingly arbitrary pattern of particle masses and mixings could reflect underlying geometric relationships in extra-dimensional space that determine these quantities through topological and geometric effects. Anomaly cancellation requirements in higher dimensional theories impose strong constraints on possible particle content and interaction patterns. These mathematical consistency requirements could explain why nature contains exactly the particle content described by the standard model, rather than other combinations that might seem equally plausible from a four-dimensional perspective. Magnetic monopoles, predicted by grand unified theories but never observed, could be confined to extra dimensions or have masses determined by extra-dimensional compactification scales. The absence of observable monopoles could be explained by geometric effects that either prevent monopole production or make monopoles too heavy to be produced at accessible energy scales. The weak mixing angle, the parameter that determines the relative strengths of Electromagnetic and weak interactions could be determined by the geometry of extra dimensions through relationships between different gauge field configurations in higher dimensional space. The specific value of this angle would emerge from geometric properties rather than being an arbitrary parameter. Higgs boson properties, including its mass and couplings to other particles, could be determined by its interactions with extra-dimensional geometry. The Higgs field might propagate partially in extra dimensions, with its couplings to matter determined by how matter fields are distributed across higher dimensional space. The number of light neutrino species, 3 active neutrinos, plus possibly additional sterile neutrinos, could be determined by the topology of extra dimensions and how many right-handed neutrino states can propagate in the bulk. Different compactification schemes would predict different numbers of neutrino species through geometric effects. Axion physics provides another connection between extra-dimensional geometry and observable phenomena. Axions could arise as geometric moduli fields associated with extra-dimensional compactification, with their masses and couplings determined by the size and shape of compactified dimensions. Axion dark matter scenarios could be naturally realized through extra-dimensional geometry. As you contemplate how extra-dimensional geometry could determine all the fundamental properties of matter and energy, recognize that this represents a profound unification of mathematics and physics. The masses of particles in your body, the strengths of forces holding your atoms together, and the patterns of interactions enabling your neural activity could all emerge from geometric relationships in spatial dimensions that exist all around you but remain beyond direct perception. Every physical constant measured in laboratories, every particle mass determined by accelerator experiments, and every coupling strength calculated from precision measurements could reflect geometric properties of 6-dimensional spaces curled up at every point in your 3-dimensional experience. The hidden geometry of extra dimensions could be the fundamental source of all observable physics. But understanding how geometry determines particle properties is just preparation for confronting the most profound question raised by extra-dimensional physics. We must now explore what it means to be conscious within a reality that extends far beyond our direct perception. Chapter 9: Consciousness and Hidden Reality if Extra Dimensions Exist All Around Us. Containing geometric complexities that determine the fundamental properties of matter and energy. Then consciousness itself emerges within and depends upon spatial reality that extends far beyond our direct perceptual access. This raises profound questions about the relationship between awareness and spatial reality, the limitations of conscious perception, and what it means to exist as a 3-dimensional mind. Embedded in a higher dimensional universe, your conscious experience operates entirely within 3 spatial dimensions. But the neural processes that generate consciousness depend on biochemical reactions, governed by particle physics that could emerge from higher dimensional geometric relationships. Every thought you have, every memory you form, and every decision you make involves quantum mechanical processes that might be fundamentally shaped by the geometry of 6 additional spatial dimensions curled up in the space occupied by your brain. The binding problem in neuroscience, how distributed neural activity creates unified conscious experience, could involve mechanisms that utilize extra-dimensional physics. If quantum coherence in microtubules or other neural structures involves higher dimensional quantum field configurations, then consciousness might literally depend on physics that extends beyond 3-dimensional space while remaining experientially confined to 3-dimensional perception. Quantum mechanics in the brain could involve extra-dimensional effects if quantum field fluctuations, entanglement, or decoherence processes are influenced by compactified dimensions. The quantum to classical transition that allows macroscopic neural states to emerge from quantum mechanical foundations. might involve higher dimensional physics that shapes consciousness without consciousness being able to directly perceive its higher dimensional substrate. The hard problem of consciousness, why there is subjective experience rather than purely objective information processing, could be related to the fact that conscious awareness operates as a lower dimensional phenomenon embedded in higher dimensional physical reality. Subjective experience might represent how three-dimensional neural activity interfaces with higher dimensional quantum field configurations that determine the intrinsic properties of matter and energy. Integrated information theory, which proposes that consciousness corresponds to integrated information in physical systems, could have extra-dimensional components if information integration involves higher dimensional geometric relationships. The phi measure of consciousness might need to account for information processing that occurs through extra-dimensional mechanisms that remain invisible to three-dimensional analysis. Free will and determinism take on new dimensions when extra-dimensional physics is considered. If quantum indeterminacy involves higher dimensional geometric fluctuations, then conscious choice might involve sensitivity to extra-dimensional processes that introduce genuine randomness or agency into neural decision-making. Alternatively, extra-dimensional determinism could constrain conscious choice through mechanisms that operate beyond three-dimensional observation. The relationship between mind and matter becomes even more mysterious when matter itself depends on higher dimensional geometric relationships. If particles, forces, and fields emerge from string vibrations in extra dimensions, then consciousness, which depends on these physical processes, represents awareness that emerges from higher dimensional reality while being confined to lower dimensional experience. Perception itself could be fundamentally limited by our three-dimensional neural architecture, even if extra dimensions exist all around us, supporting parallel universes, alternative forms of matter, or complex geometric structures. Our sensory systems evolved within three-dimensional space and lack any mechanism for detecting higher dimensional phenomena. We could be surrounded by rich extra-dimensional reality while remaining completely unaware of its existence. The anthropic principle gains new significance in extra-dimensional contexts. If countless different compactification schemes are possible, each producing different particle physics and potentially different types of consciousness, then our observation of a universe compatible with consciousness might reflect selection effects rather than fundamental design. Consciousness might exist only in specific geometric configurations of extra-dimensional space. Memory formation and storage in the brain involves complex molecular processes that could depend on higher dimensional particle physics. The quantum mechanical processes underlying synaptic plasticity, protein folding, and neural connectivity might be shaped by extra-dimensional effects that determine molecular behavior while remaining invisible to conscious introspection. About memory mechanisms, the unity of consciousness across different sensory modalities could involve extra-dimensional binding mechanisms that integrate information processed in different brain regions. If neural integration depends on quantum field effects that extend through extra dimensions, then conscious unity might literally depend on higher dimensional physics that consciousness cannot directly observe. Attention and consciousness could involve extra-dimensional selection mechanisms. If quantum measurement processes in neural systems are influenced by higher dimensional geometric fluctuations, the collapse of quantum superpositions that might be involved in conscious attention could depend on extra-dimensional physics that shapes which neural states become conscious while remaining beyond conscious access. The stream of consciousness, the temporal flow of subjective experience, might reflect how three-dimensional neural activity interfaces with higher-dimensional space-time geometry. If extra dimensions are compactified at different scales or have different topological properties, this could influence the temporal characteristics of conscious experience through mechanisms that consciousness cannot directly perceive. Altered states of consciousness, including meditation experiences, psychedelic states, and mystical experiences, could involve changes in how neural activity interfaces with extra-dimensional physics. If certain conscious states involve modified quantum coherence or different patterns of neural integration, these might provide altered access to higher-dimensional physical processes that normally remain unconscious. The possibility of consciousness in extra dimensions raises questions about whether awareness could exist in forms that don't involve three-dimensional matter. If extra dimensions support their own forms of matter and energy, they might also support forms of information processing and awareness that operate according to entirely different principles than three-dimensional consciousness. Artificial consciousness research faces additional complexity if consciousness depends on extra-dimensional physics. Computer simulations of neural networks operate according to three-dimensional physics and might miss essential higher-dimensional components of consciousness that biological systems access through their quantum mechanical substrate. True artificial consciousness might require technology that can interface with extra-dimensional physics. The relationship between individual and cosmic consciousness takes on new meaning if consciousness emerges within higher-dimensional reality. Individual awareness could represent localized patterns in higher-dimensional information processing systems, with apparent separation between different conscious entities reflecting limitations of three-dimensional perception rather than fundamental isolation. Death and personal identity face re-examination in extra-dimensional contexts. If consciousness depends on higher-dimensional quantum field configurations, then the cessation of three-dimensional neural activity might not represent complete termination of the conscious pattern if higher-dimensional aspects of the system persist. Alternatively, extra-dimensional physics might ensure that conscious patterns are more fragile than three-dimensional analysis suggests. The meaning and purpose of consciousness within higher-dimensional reality becomes a profound philosophical question. If aware beings like humans represent three-dimensional shadows of higher-dimensional physical processes, then conscious experience might serve functions in higher-dimensional reality that we cannot comprehend from our limited three-dimensional perspective. Communication between conscious beings could involve extra-dimensional components if quantum entanglement or other non-local quantum mechanical effects play roles in neural function. Telepathic or other anomalous conscious phenomena, if they exist, might involve extra-dimensional physics that allows information transfer through mechanisms that bypass three-dimensional space. The evolution of consciousness might reflect the optimization of three-dimensional neural systems for interfacing with higher-dimensional physics. Natural selection could have favored neural architectures that most effectively access extra-dimensional quantum mechanical resources while remaining embedded in three-dimensional biological systems. Religious and spiritual experiences could involve enhanced sensitivity to extra-dimensional physics if certain conscious states modify the relationship between three-dimensional neural activity and higher-dimensional quantum field configurations. Mystical experiences of unity, transcendence, or connection to larger realities might reflect direct conscious access to higher-dimensional aspects of physical reality. The future evolution of consciousness might involve developing technologies or biological modifications that provide enhanced access to extra-dimensional physics. Brain-computer interfaces, genetic modifications, or other enhancements might eventually allow conscious beings to perceive or interact with higher-dimensional reality more directly than current three-dimensional consciousness allows. As you contemplate your existence as a conscious being potentially embedded in higher-dimensional reality, consider that every moment of awareness represents an extraordinary phenomenon. Three-dimensional consciousness emerging from and depending upon spatial reality that extends far beyond conscious access. Your thoughts about extra dimensions themselves emerge from neural processes that might depend on the very higher dimensional physics that consciousness cannot directly perceive. The mystery of consciousness becomes even deeper when consciousness exists within hidden spatial reality. Awareness represents not just the hard problem of how subjective experience emerges from objective processes, but how three-dimensional subjective experience emerges from processes that might fundamentally occur in higher dimensional space that consciousness cannot access, understand, or even imagine. But consciousness represents just one perspective on extra-dimensional reality. We must now confront the ultimate implications of what it would mean to live in a universe where the majority of spatial reality remains forever hidden from direct observation. Chapter 10. The Hidden Universe If Extra Dimensions Exist. They reveal that our three-dimensional experience represents only a tiny fraction of spatial reality, like perceiving the shadow of an enormously complex higher dimensional universe that extends through geometric configurations we cannot visualize, explore, or comprehend. This possibility transforms our understanding of existence itself, suggesting that we inhabit not the universe, but a narrow-dimensional slice of a vastly larger and more complex reality that remains forever beyond direct access. The scale of dimensional hiding is staggering when fully considered. If string theory requires 9 spatial dimensions plus time, then our familiar three-dimensional space represents only 1/3 of total spatial reality. 6 additional spatial dimensions could exist at every point around you, containing geometric structures, physical processes, and potentially forms of matter and energy that operate according to laws and possibilities that three-dimensional physics cannot encompass or predict. The landscape of possible compactification suggests that our observable universe represents just one geometric configuration among an astronomical number of possibilities. Current estimates suggest there could be 10,500 or more mathematically consistent ways to compactify extra dimensions, each corresponding to a different possible universe with different particle physics, force strengths, and physical constants. We might inhabit one tiny corner of a vast multiverse where most reality operates according to entirely different physical principles. Parallel universes could exist just millimeters away in there's extra-dimensional space, completely inaccessible from our three-dimensional perspective, but as real and complex as our own cosmic domain. These parallel realities might contain different forms of matter, alternative evolutionary pathways, and perhaps consciousness types that operate according to physical principles that differ radically from three-dimensional experience. While sharing the same higher dimensional space, the vast majority of possible particle physics configurations would be incompatible with the existence of complex structures, stable atoms, nuclear fusion, or biological evolution. If extra-dimensional compactification determines particle properties, then the apparent fine-tuning of physics for complexity and consciousness might reflect selection effects, rather than design consciousness necessarily observes. Universe where extra-dimensional geometry supports conscious existence. hidden forces and interactions could operate through extra-dimensional mechanisms that remain completely invisible to three-dimensional observation. While electromagnetic, weak, and strong nuclear forces appear confined to our three-dimensional brain, other fundamental forces might propagate through extra dimensions, creating rich interaction networks between particles and fields that we cannot detect, but that fundamentally shape the behavior of matter and energy. Dark matter and dark energy, comprising about 95% of the universe's total energy content, could be explained through extra-dimensional physics. Dark matter might consist of particles that interact primarily through extra-dimensional forces, while dark energy could emerge from the dynamics of extra-dimensional geometry or interactions between our universe and parallel branes in higher dimensional space. The holographic principle, emerging from black hole physics and string theory, suggests that all information contained within any volume of space can be encoded on its lower dimensional boundary. If true, this would mean that our three-dimensional experience might be a holographic projection of more fundamental information processing occurring in higher dimensional space, making our apparently solid reality emergent from extra-dimensional phenomena. Archaeological evidence from particle physics. Experiments might already contain signatures of extra-dimensional reality that we lack the theoretical frameworks to recognize. High-energy collision data, precision measurements of particle properties, and astronomical observations might contain patterns that would reveal extra-dimensional physics if we develop better analytical tools for recognizing higher dimensional signatures. The future of scientific discovery could involve developing technologies that provide indirect access to extra-dimensional physics through their effects on three-dimensional phenomena, gravitational wave astronomy, precision tests of fundamental constants, and increasingly sophisticated particle accelerator. Experiments might eventually reveal the hidden extra-dimensional architecture that shapes observable reality. Time itself could have extra-dimensional components if string theory scenarios involving multiple time dimensions are realized in nature. While we experience one temporal dimension, higher dimensional space-time might contain additional temporal directions that create complex causal structures and temporal relationships that three-dimensional consciousness cannot access or comprehend. The ultimate fate of the universe takes on new meaning in extra-dimensional scenarios. Cosmic evolution might be driven by extra-dimensional dynamics that determine whether our universe expands forever, recollapses, or undergoes phase transitions that fundamentally alter the relationship between three-dimensional space and higher-dimensional geometry. Our cosmic future might depend on processes occurring in dimensions we cannot observe. Technological limitations might prevent us from ever directly accessing extra-dimensional reality, regardless of future scientific advances. If extra dimensions are compactified below the Planck scale or hidden through mechanisms that make them fundamentally unobservable from three-dimensional perspectives, then higher dimensional reality might remain forever beyond direct scientific investigation. While continuing to determine the properties of observable physics, the relationship between mathematics and physical reality becomes even more mysterious when most physical reality occurs in extra dimensions. Mathematical descriptions of higher dimensional spaces might provide our only access to the geometric structures that determine fundamental physics, making mathematics not just a tool for describing nature but the primary means for exploring the hidden reality that shapes existence. Conscious beings throughout the universe might all share the limitation of being confined to lower dimensional spaces while depending on higher dimensional physics for their existence. Extraterrestrial intelligence, if it exists, might face the same barriers to accessing extra-dimensional reality, making the hidden universe a universal limitation that constrains all conscious observation regardless of technological sophistication. The meaning of exploration and discovery transforms when most reality remains hidden in extra dimensions. Traditional exploration involves moving through three-dimensional space to encounter new regions or phenomena. But extra-dimensional exploration might require developing conceptual and mathematical tools for understanding spatial reality that cannot be visited, observed, or directly manipulated through three-dimensional actions. Religious and spiritual traditions that emphasize hidden realities, transcendent dimensions, or levels of existence beyond ordinary perception might reflect intuitive recognition that spatial reality extends beyond direct experience. If extra dimensions exist, then mystical traditions pointing toward hidden aspects of reality might represent primitive but valid insights into the true complexity of existence. The question of whether we are alone in the universe becomes more complex when extra dimensions are considered. Even if three-dimensional space contains no other intelligent life, higher dimensional space might support forms of consciousness and intelligence that operate in ways we cannot imagine or detect. We might be surrounded by rich communities of extra-dimensional beings while remaining completely unaware of their existence. Scientific humility becomes essential when contemplating extra-dimensional reality. Our most sophisticated theories and experimental techniques probe only the three-dimensional surface of potentially vast higher-dimensional reality. The confidence with which we describe physical law, cosmic evolution, and the fundamental nature of existence might be analogous to flatland beings, confidently describing three-dimensional reality based solely on two-dimensional observations. The philosophical implications of hidden dimensions challenge anthropocentric assumptions about cosmic significance. If our three-dimensional universe represents a tiny fraction of total spatial reality, then human consciousness, terrestrial evolution, and even cosmic history might be peripheral phenomena within a vast higher dimensional landscape where the most significant processes and developments occur in dimensions we cannot access. Beauty and truth in science take on new meaning when most reality remains hidden. The mathematical elegance of theories describing higher dimensional physics might provide our most reliable guide to understanding hidden reality, making aesthetic criteria for evaluating scientific theories more important than direct empirical verification when dealing with fundamentally unobservable phenomena. The future of human understanding might depend on developing new cognitive tools, mathematical frameworks, or technological enhancements that provide better access to extra-dimensional reality. Brain-computer interfaces, artificial intelligence, or other cognitive technologies might eventually allow human minds to process higher dimensional mathematical structures and thereby gain enhanced understanding of hidden reality. As you contemplate the possibility that you exist within a hidden universe that extends far beyond your three-dimensional experience, recognize that this represents both a humbling and inspiring perspective. Humbling because it suggests that conscious experience accesses only a tiny fraction of spatial reality. Inspiring because it suggests that reality possesses geometric complexity and richness that exceed our current imagination. Every point around you could contain six-dimensional geometric structures of extraordinary mathematical beauty and physical significance. Every particle in your body could be vibrating through spatial dimensions that your consciousness cannot perceive, but that determine every aspect of your physical existence. You could be embedded in a cosmic reality that extends through geometric configurations so complex and beautiful that they exceed the descriptive power of any conceivable language or artistic expression. The universe might not be hiding dimensions from us maliciously or accidentally, but because the three-dimensional interface represents the natural boundary between accessible and inaccessible reality, for consciousness evolved within three-dimensional space. The hidden dimensions might be forever beyond direct experience, not as a limitation, but as an essential feature of what it means to be conscious within higher dimensional reality. Throughout this exploration of hidden dimensions, we've discovered that reality might extend far beyond the three spatial dimensions that define our direct experience. Through geometric structures so complex and beautiful that they exceed our ability to visualize, while fundamentally determining every aspect of the physics that makes existence possible. But perhaps the most profound realization isn't that extra dimensions might exist. It's what their existence would reveal about the relationship between consciousness and cosmic reality. If 6 additional spatial dimensions exist at every point around you, curled up into geometric configurations that determine particle masses, force strengths, and the fundamental constants that enable complex matter, then your conscious experience represents awareness that has emerged within and depends upon spatial reality that extends infinitely beyond conscious access. You exist not as a being within the universe, but as consciousness embedded in a narrow dimensional slice of vastly more complex, higher dimensional reality. The mathematics we've explored, string theory's requirements, compactification mechanisms, Calabi-Yau geometries, aren't abstract, theoretical constructs, but potentially the actual geometric foundations of your existence. Every thought you have emerges from neural processes that depend on quantum mechanics, and that quantum mechanics might emerge from string vibrations in 6 dimensions curled up in the space occupied by your brain. Your consciousness represents 3-dimensional awareness of processes that fundamentally occur in 9-dimensional space. As you continue your life after learning about hidden dimensions, remember that every physical interaction you experience molecular bonds holding your body together, electromagnetic forces enabling your neural activity, nuclear fusion powering the sun could emerge from geometric relationships in spatial dimensions that exist all around you but remain forever beyond direct perception. The apparent solidity of 3-dimensional matter might be emergent phenomena arising from higher dimensional geometric complexity. The weakness of gravity that allows you to lift your hand against Earth's gravitational field demonstrates how forces diluted through extra dimensions appear weak compared to forces confined to 3 dimensions. Every time you experience gravity's weakness, you're experiencing potential evidence for spatial dimensions your senses cannot detect, but that fundamentally shape every aspect of physical reality. You are not separate from the hidden dimensional reality we've explored. You are consciousness that has emerged from the interaction of particles and forces that potentially derive their essential properties from the geometry of extra dimensions. Your thoughts about hidden dimensions themselves emerge from neural processes that might depend on the very higher dimensional physics that consciousness cannot directly observe. The possibility that parallel universes exist just millimeters away in 4th, 5th, or 6th spatial dimensions means that you could be sharing the same location with entirely different forms of matter, energy, and potentially consciousness that operate according to physics determined by alternative compactification geometries. Reality around you might be far richer and more complex than 3-dimensional experience reveals. If extra dimensions exist, they transform the meaning of exploration and discovery, from journeys through 3-dimensional space to investigations of mathematical structures that describe geometric reality beyond visualization. The cutting edge of human understanding becomes not traveling to distant places, but developing the mathematical and conceptual tools needed to comprehend spatial reality that extends beyond dimensional limitation. The experimental hints we've examined: missing energy at particle accelerators, gravitational tests at microscopic scales, astronomical observations of dark matter and dark energy might represent humanity's first glimpses of higher dimensional reality. We could be living at a historic moment when consciousness first detects evidence for spatial dimensions beyond direct experience, revolutionizing our understanding of the fundamental nature of existence. The relationship between mind and reality becomes even more mysterious when reality itself extends through dimensions that consciousness cannot access. Subjective experience represents not just a hard problem of how awareness emerges from objective processes, but how three-dimensional consciousness emerges from objective processes that potentially operate in higher dimensional space that consciousness cannot perceive, understand, or imagine. But perhaps the deepest insight about hidden dimensions is this: they would not represent obstacles preventing us from understanding reality, but revelations about the true richness and complexity of existence within which consciousness finds itself embedded. The geometric complexity of six-dimensional Calabi-Yau manifolds, the mathematical elegance of string theory, and the profound connections between higher dimensional geometry and observable physics suggest that reality possesses mathematical beauty and structural sophistication that exceed our current comprehension. The universe isn't hiding dimensions from us as a conspiracy or accident, but because dimensional hiding represents the natural relationship between consciousness and spatial reality. Three-dimensional consciousness emerges within higher dimensional space as the interface between accessible and inaccessible reality, between the observable and the hidden, between direct experience and fundamental truth. If you found this exploration of hidden dimensions enlightening, consider sharing these ideas with others who might appreciate understanding the potential geometric complexity of spatial reality. Like this video if the possibility that 6 additional dimensions surround you right now expands your sense of cosmic wonder. And subscribe for more investigations into the mathematical foundations of existence. Check out my exploration of how consciousness might interface with quantum mechanical reality in your mind might be quantum. You'll discover connections to tonight's journey that reveal even deeper relationships between awareness and the fundamental structure of reality. Remember this as you move through your daily three-dimensional experience. Every step you take might carry you through spatial dimensions you cannot perceive. Every breath you take might involve air molecules vibrating through geometric structures that exceed imagination. And every thought you think might emerge from neural processes that depend on the hidden complexity of higher dimensional space. You are not a three-dimensional being accidentally trapped in three-dimensional space. You are consciousness that has emerged within higher dimensional reality as the universe's way of becoming aware of its own hidden geometric complexity from the inside. The dimensions the universe might be hiding from us aren't separate from us. They are the invisible foundation upon which our existence depends and through which awareness becomes possible within cosmic reality that extends far beyond direct experience into mathematical structures of extraordinary beauty and profound mystery that consciousness can contemplate, but never directly perceive.